Hello. In this video we are going to learn Quicksort, which is the most popular sorting algorithm. Quicksort is popular because it's easy to implement, it works well for a variety of input data, and it's substantially faster than any other sorting algorithm. Quicksort is a in-place algorithm. Its efficiency in the average case is n log n. So let's look at Quicksort and then we'll look at its implementation and then we'll talk about its efficiency. So let's look at this diagram. There are three steps in Quicksort. The first step is choosing a pivot. So for example, this is the array that we want to sort. So initially we'll choose first element as a pivot. There are different strategies in choosing a pivot. For example, you can choose first element as a pivot, as we are doing in our case. You can also choose a last element as a pivot, or you can also randomly choose any other element as a pivot. When we will look at the efficiency of Quicksort, we'll talk more about this again. So once you have chosen a pivot, the next step is to rearrange the elements so that the numbers which are less than the pivot are on the left side and the numbers which are greater than the pivot are on the right side. So we are actually partitioning the array based on the pivot. So once we have done the partitioning, we have basically divided the original array into two subarrays. Since Quicksort is a divide and conquer algorithm, we divide the arrays into smaller chunks and then we use partitioning method as a conquer step to repeat that process. So once we repeat the process, eventually we get the sort array. So that's a overview of the Quicksort. So let's now look at an actual example. So what we are going to do is, again, we are going to choose the first element as a pivot, then we are going to partition the array into two subarrays so that elements which are less than or equal to pivot will be on the left side of the pivot, and elements which are greater or equal to pivot will be on the right side. So let's look at this input list. So this is the list that we want to sort. So this is currently an unsorted array. Using Quicksort, we will sort this array. So first step is to choose the pivot element. In our case, we are going to choose first element as a pivot. So once we have chosen the pivot, what we will do is we will now do the partitioning so that elements which are greater than the pivot are on the right side and elements which are lesser than the pivot are on the left side. So to do that, we will use two pointers. So we will use two pointers. The first one, let's call it left selector, and let's call the second pointer as right selector. Now that we have two selectors, let's look at how these two selectors are going to work. So the left selector's job is to find element which is greater or equal to the pivot, and the right selector job is to find element which is smaller or equal to the pivot. So to do that, left selector will start scanning until it finds the element which is greater or equal to the pivot. Similarly, the right selector needs to find element which is smaller or equal to the pivot. So in this case, the right selector is already pointing at 2, and since 2 is less than 19, right selector won't move anywhere. It will stay at this location. When this happens, we swap the values pointed by left and right selector. So 2 and 35 will get swapped. Left and right selector are still there, but the values pointed by these two pointers are now swapped. So there are two swap conditions that we need to remember in Quicksort. The first one is when the left selector is less than the right selector, which is this case. In that case, we are swapping the values pointed by left and right selector. The left selector was here and right selector was here. We swap 2 with 35. which is the first case that we need to remember. There is another case that we need to remember is when left selector is greater or equal to the right selector. In that case, we actually need to swap the value pointed by right selector and pivot. So we'll talk about this second condition when that happens in this array. Right now, just remember this first condition where left selector is less than the right selector. So again, we continue doing this process. So again, left selector will try to find element which is greater than the pivot. So 23 is greater than 19, so it will go and stop here. And the right selector will try to find the element smaller. So it will come to number 14 because it is smaller than 19. Now notice here in this case, left selector is actually greater than the right selector. So that's the second condition. So when that happens, we swap the value pointed by right selector with the pivot. Now one thing that you should note here is the values which are greater than 19 are on the right side and the values which are smaller than 19 are on the left side. So that's why we are using this left and right selector, so that we are pushing the values which are greater to the right and we are pushing values which are smaller to the left. And as we continue doing that, eventually we will end up with a sorted array. When this second condition happens, we stop the partitioning. So our partitioning process is now complete. What has happened now is we have partitioned the original array into two sub-arrays, and 19 is at its correct location in the final sorted array. So 19 will not move anywhere after the partitioning. Now we are going to repeat the same process on these two sub-arrays. We have these two sub-arrays and we are going to apply same method that we have seen again. So we'll again choose two new pivots. For this sub-array, we'll choose the first element as a pivot, which is 14, and for this sub-array we'll choose 23 as a pivot. And then again we will have left and right selector for both of these sub-arrays. So let us work on the first sub-array. So again 14 is pivot, we have the left selector which is the next element to the pivot, and we have the right selector as a last element. So left selector needs to find element greater than the pivots. So we need to find element greater than 14. So as we do here, there is no element which is greater than 14, so left selector goes until the last element, and since there are no more element left, it will stop here. So in that case, you can see here we have come to the second condition where left selector is greater or equal to the right selector. So when that happens, we swap the value pointed by right selector with the pivot. So we swap pivot with the value pointed by right, and then we stop the partitioning. So in that case, now we have divided our sub-array into another sub-array where we have 3 elements and 0 element. Now let us continue the same process. Again, we will choose the first element as a pivot, and we'll have 2 selectors. We need to find element greater than the pivot, so left selector will stay here and the right selector will try to move until here. So the right selector will try to find element which is smaller or equal to pivot, so it will come to the pivot. Since in that case left selector will be greater than the right selector, since right selector will be pointing at pivot, we will swap the value 2 with 2, or you can say we'll just stop there, and then the array will be again partitioned. So now we have another sub-array of size 2. So we will again use left and right selector. In this case, left selector needs to find element greater than the pivot, but there are no more elements on the right side, so it will just stay there. And right selector needs to find element smaller than the pivot, so again it will stay there because 3 is already smaller than 5. So in that case, since left selector is greater or equal to right selector, we will swap value pointed by right selector with the pivot. So the first half of the main array is now sorted. Let's now apply the same process on the second subarray. So we will choose first element as a pivot. We'll have again left selector and right selector. Left selector needs to find element greater than the pivot, so 24 is it already greater than the pivot, and right selector needs to find element smaller or equal to the pivot, so it will go up to here. And again, now in this case, this second condition is true, where left selector is greater or equal to the right selector. In that case, we swap the value pointed by right selector with the pivot. Since right selector is already pointing at pivot, we don't have to specifically swap the value. And then that means we are done here partitioning, and now we have divided this array into subarray as shown here. So subarray of size 3 and subarray of size 0. So let's now work on this subarray. So again, we choose the first element as a pivot. We have two selectors. We need to find greater number using the left selector. So 43 is greater, so it will stay here, and this needs right selector needs to find the smaller, so it will go all the way up to the pivot. And again, we meet the second condition. Since these two have crossed and it is greater than the right selector, we swap the value pointed by right selector with the pivot. So we end up with array of size 2. So again, we choose the first element as a pivot, and then we have two pointers. We need to find element greater than the pivot with the left selector, so it will just stay here, and the right selector needs to find the element smaller, so it will also stay here. And in this case, this again, the second condition is true, so we'll swap the value pointed by right selector with the pivot. So 35 will get swapped with 43. Alright, now we have finished sorting our second subarray. So this is how our fully sorted array looks like using Quicksort. So let us now try to implement Quicksort using Python. I am right now using PyCharm IDE. We are going to write implementation of Quicksort here. So let's look at the one unit test that I have written to test the implementation of our Quicksort. In this unit test, first I am generating 10 random numbers. Then I am sorting those using inbuilt sorting algorithm. Reason for that is we need to compare the result of our Quicksort with the inbuilt sorting algorithm. That way we can make sure our Quicksort is actually sorting correctly. So that's what we do here. In the last line, we compare result written by our Quicksort by the inbuilt sorting algorithm. Now let us write our Quicksort here, and then we will run this unit test. First we need a function. Let's call it Quicksort. This function is going to accept input list, and then we will also pass the left and right pointers. Alright, so let's look at again how Quicksort works. First, we are going to use partitioning algorithm to partition the array such that elements less than pivot are on the left side and elements greater than the pivot are on the right side. So first step would be to partition or call the partition function. Then we are going to recursively call same algorithm on these two subarrays. Let's try to do that in Python. we are going to call partition method, which will return us a pivot. So we'll get pivot from partition method. Then once we have the pivot, we are going to recursively call quicksort on the left and right subarray. Since quicksort is in place sorting algorithm, we are going to use the same input list. Here we are calling quicksort recursively on the left subarray first. Since pivot will be at its correct location in the final sorted array, we don't need to include pivot anymore when we are recursively calling quicksort on the left and right subarray. So here we are calling quicksort recursively on the left subarray after the partitioning, and then we are calling quicksort on the right subarray. So we'll have to start with pivot position +1 and then go up to the right. So that's the skeleton of our quicksort. Since quicksort is a recursive algorithm, we need to write a base case so that we don't run into an infinite loop. So let's add a base condition. So if left is greater than or equal to right, that means there are no more elements left for us to partition. We will return. So that's our base case. So now let's try to add the partition method. So let's define another function called partition. The partition function will also take input list. Also it will take left and right values so that we will know what's beginning and the end of our list. Let's look at again how the partitioning algorithm works. What we do for the partitioning is first we choose the first element as a pivot, then we use two selectors, left selector and right selector. Let's try to do that. We'll first choose the pivot, which is going to be the first element. So pivot will be left, which will be the first element. Then we will create a left selector that will be pointing to the element next to the pivot, so pivot +1 or left +1, and then we will create a right selector which will be pointing to the right. So let's again look at how the left and right selector are going to work. So the left selector job is to find element greater than the pivot. So left selector will keep moving ahead one location at a time until it finds the element greater than the pivot, and right selector job is to find element smaller than the pivot, so it will keep moving in the left direction. Now let's try to write logic for left selector. So while input list left selector is less than or equal to input list pivot, increment the left selector. So we are actually incrementing the left selector until we find the element greater or equal to the pivot. So similarly we can do this for right selector. So input list right selector is greater than or equal to input list pivot, right selector -1. So we'll decrement the right selector. So we are moving the right selector to the left until we find a smaller element or equal element to the pivot. We have now written logic for left and right selector. Now let us try to implement these two conditions. The first condition is when the left selector is less than the right selector, we will swap the values pointed by left and right selector. So let us implement that logic here. So if left selector is less than right selector, we are going to swap the values pointed by left and right selector. Alright, now we will try to implement the second condition. The second condition is when a left selector is greater or equal to the right selector, we swap the value pointed by right selector with the pivot. So let's try to implement this. Else if left selector is greater than or equal to right selector, swap the values pointed by right selector with the pivot. After we are done swapping values pointed by right selector with the pivot, we end our partitioning algorithm and then we return the pivot position so that we can recursively again apply quicksort on the two subarrays. So let us return the pivot position. Because pivot is now swapped with the right selector. Now let us add some base condition in our partitioning algorithm. So as we know here, the left selector and right selector will keep moving until both of these cross. So let us now implement the logic where left and right selector are moving until they cross each other. Now let's go back to our editor. Let's add a condition here. So we want to repeat this logic until the two selectors are crossed. So while right selector is greater than or equal to left selector, we will repeat this process. Let us now implement the logic where left selector does not find any element greater than the pivot and then moves to the right or to the end of the list. So we need to add this condition so that we don't go out of bounds while the program is running. So let us now add bound checking for the left selector. We don't want left selector to go beyond the limits. So let's say while left selector is less than right, and so that way left selector will not go past the limit. Similarly, we will add bound checking for the right selector. So let's add another condition here. While right selector is greater than left, so this will make sure that we won't go below the left or say the first element in the list. So now we are done with writing our partitioning algorithm, and we also have our quicksort here. So let's now test this algorithm using the unit test that we wrote before. So let's run this. So as you can see, we have passed our unit test. This was the random list that was generated, and then our quicksort returned this sorted list, and then we match that with the existing algorithm, and then since those two lists are equal, we have passed our test. So let's run this for several iterations just to make sure that we have not missed any edge case. So let's run this by clicking here. We could also write another unit test where we could run multiple iterations, but for now I'm just going to give it a run. You can also change the size of the input and do some variations, and then we can also see that our Quicksort works on large list as well, so it's sorting correctly. So let's give it a run, more run. So if in any case if the test result fails, that means there is a bug in our Quicksort implementation, and in that case we would need to fix that. If you are interested in visualizing the execution of this algorithm, you can put breakpoints here, and then you can start debugging. And then using step over and step 2 options, you can run this algorithm step by step. You can add different variables or expressions in the watch list if you want to monitor the values. For example, if you want to monitor whether right selector is moving correctly or not, or whether the value pointed by right selector is equal or greater to the pivot, so you can add such expressions here, and then you can step by step use those debugging techniques to make sure your algorithm is working correctly. Alright, let's look at efficiency of Quicksort. So Quicksort is the most popular sorting algorithm. Still, in the worst case, it runs in big theta of n square. So let's look at why is that. So Quicksort performs worse when the array is already sorted. So let's see why is that. So let's say this is your input array and the array is sorted. So what will happen is each time we'll be doing partitioning at the first location. So if you have to guess the efficiency of Quicksort, what will happen is initially we'll be doing n comparisons. In the next step we'll be doing n minus 1 comparison, and so on. So because of the array is partitioned at the first location, if we try to add all that up, it comes to a series, and if we solve that series, the answer comes to big theta of n square. There is also another way we can calculate this by working on a small array and then calculating the number of comparisons done. Let's say we take a list of 4 elements, and then if we apply our algorithm by using left and right selector, you will find that initially we'll be doing 5 comparisons for the list size of 4. Then when the list size gets reduced to 3, we'll do the 4 comparisons. When the list size is 2, we will do 3 comparisons, and then when there is only a pivot left or a list size 1, we'll not do any comparison. So if we add this into an equation, this is how it will look like. We do 3 comparisons when the list size is 2, and then for any list of size n, we'll do n plus 1 comparison. So if you solve this equation, the answer again comes to big theta of n square. So the Quicksort's efficiency in the worst case is big theta of n square. If you are interested in knowing how to solve this equation, I have those steps here. I'm not going to go into detail, but if you're interested, you can pause this video and then look at this calculation. But basically we are just solving this using the arithmetic series, and then we just simplify this and then eventually we come to this equation by just simplifying the terms, and then at the end we will just take the largest contributing term, and that's how we come to the answer n square. So the worst case efficiency of Quicksort for any input size will be big theta of n square. We can also find the worst case efficiency of Quicksort by using a recurrence relation and solving that by using a backward substitution method. Since Quicksort is a recursive algorithm, it can be represented using a recurrence relation. So this is how the recurrence relation for Quicksort looks like in worst case. Here we have divide part, and then here the conquer part, which is our partition function. So partition function in the worst case is doing n comparisons, and then in the worst case also, since we are splitting pivot at the first location, we are dividing array into n-1 elements. So if we solve this recurrence relation using backward substitution method, we eventually come to the same answer, that Quicksort in the worst case takes big theta of n square. Alright, now let's look at the best case of Quicksort. So the best case of Quicksort will happen if somehow we always split the array in the middle. So if we do that, the recurrence relation in that case will look like this. Since we are splitting array into half each time n by 2, and then we have such two sub arrays, this is how the recurrence relation will look like for Quicksort in the base case. Now we can solve this recurrence relation using the master method. So if you are interested, you can look online more about the master method. I'm not going to cover details about master method, but if you use the master method, then you can very easily solve this recurrence relation, and your answer for the base case efficiency of Quicksort will come to big theta of n log n. If you are interested in knowing the average case analysis of Quicksort, you can look online. There are various resources where you can understand how the average case analysis of Quicksort is done. It is more involved, so I'm not going to cover that here, but if you're interested, you can look online. There are really good resources on understanding how the average case analysis of Quicksort is done. This is how the complexity of Quicksort looks like as compared to merge sort, insertion sort, and bubble sort. So in real life situations, we are mostly interested in looking at the average case efficiency. So Quicksort works in big theta of n log n in the average case, and that's why Quicksort is very popular and commonly used sorting algorithm.